So hi everybody, I'm Thomas Gilray, and I'm going to be talking about a couple of related approaches that I've been exploring just this summer with a collaborator, Siddharth Kumar, whose expertise is in parallel algorithms and parallel I/O, toward accelerating control flow analyses by extracting some of their parallelism in a principled way using Datalog, MPI, and CUDA. So what is control flow analysis? Well, if we wanted to perform a traditional data flow analysis in the context of a language like Scheme, maybe to do constant propagation or detect aliases or something like this, then we might model the propagation of a value into a variable x and through a syntactically known function into another variable y. But then what happens if we reach a call site where we invoke g on y? Well, we have to know what g could be in order to know where y is going to propagate next, where control propagates and what y could be, what the value in y could get bound to. And conversely, at the top of this function, if we have a function f which accepted x as a parameter, we have to know what, at what call sites f might have been invoked in order to know what values could flow into x in this function. So control flow analysis is really the name for flow analysis generally in a higher order setting, because we have an entanglement of control flow and data flow, and in order to get an analysis with some precision and soundness simultaneously, we need to do a simultaneous modeling of both of these concerns. And this can form the basis for a number of heavyweight whole program analyses, which could potentially give us strong information about that can be used to verify components of our program, or could be used to optimize our program. So for example, flow-directed inlining, or higher order symbolic execution, escape analysis, detecting when we could turn a full continuation into an escape continuation or something like this. And so if this is all heavyweight and powerful, it must be very slow, right? And so the next question we asked is, how might we parallelize this in a principled way? Surely there's parallelism in this problem, because we have a number of concerns that we're modeling simultaneously. And as we lose precision in an analysis like this, we have some non-determinism. We don't know what's going to happen. And so we have to model multiple different possibilities. And so all of this is going to introduce parallelism that we should be able to exploit in modern hardware. So we envision a pipeline for doing this in a principled way that starts with a concrete semantics or an interpreter, which we can develop in a systematic way into an approximate or abstract semantics or a static analysis. And a good example of this, which I'll talk about in the background, is the abstracting abstract machines methodology. And then we would take this static analysis and we want to encode it in Datalog. And this is great both so that we can optimize the problem, and also so that we can isolate the concern of designing our static analysis from the concern of how we solve it in a performant way. And a good example of this is the dupe framework by Smaragdakis and some of his collaborators. So he doesn't have, he has more of an ad hoc way of writing the semantics to begin with, but he has a very systematic way of turning it into Datalog in a way that's tunable and has some knobs that you can adjust. And then Datalog can be solved in a bottom-up manner using fast relational algebra primitives. And good examples of this would be the B2D library, which uses binary decision diagrams to both encode relations and then also algebra on those relations, manipulations of the relations that can be used to encode solutions to Datalog. One of the problems here is that binary decision diagrams are compressed, but it depends heavily on variable ordering. So in the best case, they could be much more efficient, but in the worst case, they could also be much less efficient, up to an exponential blowup. And so a lot of work has actually gone into how to use machine learning algorithms to figure out what kind of variable ordering we want to use for BDDs. And so I think this is not as appealing of an approach for that reason, perhaps. Soufflé is a very recent implementation of a semi-naive bottom-up solver that really just uses very fast underlying trie-data structures to directly propagate tuples between relations. And then they use a partial evaluation approach to optimize the problem and write it out into C++. And what we'd really like is to be able to encode, is to be able to exploit parallelism at the level of these relational algebra operations. And there's two promising recent approaches that we're interested in building on top of. So one of these is a paper from the beginning of this year, which describes a distributed hash join algorithm for implementing joins across many nodes using MPI. And so they scale a single join operation up to a couple thousand nodes, but they don't do fixed point computations or anything like that. Another approach is this Redfox library, which encodes a bunch of relational algebra primitives for general purpose GPU programming in CUDA. So that's another approach we try to build on. And a number of recent supercomputers are increasingly using heterogeneous architectures which combine traditional CPUs with coprocessors. And so perhaps if both of these are promising, we could even explore a hybrid approach. So I'll be talking about a bit of an eclectic mix of some of these topics. I'm going to focus a bit on background to begin with and talk about abstracting abstract machines and focus on the functional aspect of this. And then I'll talk about Datalog and transitive closure in Datalog. And we can think of transitive closure as kind of the heart of a CFA algorithm, because essentially a CFA algorithm is exploring the ramifications of constraints that are in our program. And so it's kind of like an entangled set of different transitive closure operations that we have to perform to figure out how different things propagate through our program. And then we'll talk about relational algebra and then these two approaches, and it's very much ongoing work, so I'll talk about some of the future work that we envision for this. So abstracting abstract machines is a very general approach to systematically turning a concrete semantics into an abstract semantics. And since we're all fans of scheme here, I thought we'd start with talking about formal semantics in the form of scheme interpreters. So let's say we have an interpreter for the lambda calculus, which accepts an expression in an environment. And so we might case split on our three different forms. And these first two, we return a closure, or we return a value that's in our environment. And then in the case of an application, we go and evaluate our two different sub-expressions, and then we match on the closure we get back for the value in call position, and then we go and make a tail call to our interpreter again. And so if we want to think about how we would finitize this semantics and turn it into a static analysis, we might notice that we're basically taking one big step from an E in an environment to another expression environment, where in between we have to worry about direct recursive calls to our interpreter. So in an abstract machine semantics, we would have a program state like this, an E in an environment, that's a call site, that's stepping to another one. But in the process of computing this transition, we have to worry about how do our two sub-expressions evaluate. And so if we want to finitize this, we have to worry both about finitizing it at all these different levels, right? So in all different possible evaluation contexts. So the first step that we might take is to use a small step semantics, to transform this into a small step semantics, which basically is to turn our interpreter into a continuation passing style interpreter. And so I won't explain in detail how this works, but I'll kind of refresh your memory if you've seen this before. So basically we take a continuation and we dispatch, instead of returning our values, we dispatch on a helper function which executes calls our continuation. And then we make a call to our first sub-expression with a continuation, and then we have a helper which handles our two continuations by calling back into the interpreter. So now we have these two mutually tail recursive functions. So now we can take a expression and we can inject it into an initial state, and then we can iterate this one loop on this initial state to explicate the full evaluation of our program. And so what we've done is we haven't removed the unboundedness in our program, but we've sort of concentrated it. We've taken unboundedness that exists in all possible evaluation contexts and focused it into this one big fixed point loop. So we might not have a fixed point loop that we can compute in a finite number of steps, but we do have a fixed point that we can approximate using the tool of abstract interpretation. So why is this unbounded specifically? We know the lambda calculus is Turing complete, but if we had the omega function, while it might run forever in the concrete evaluator, we could still model it as a self loop. And so we dig into why this is unbounded. We'll see that our environment maps variables to closures, and closures are expressions in environments, which then in turn are maps from variables to closures. So we can arbitrarily deeply nest our environments, and we can build up new states. And so the strategy that's proposed by Matt Might and Abstract Interpreters for Free is to cut this direct recursion by introducing a store passing style transformation that gives us a set of addresses that we can finitize. Yes, we'll be talking here later. So if we happen to snip it at this edge, then we get a standard store passing style transformation. So what that gives us is an environment that maps variables to addresses, and then a store that maps addresses to closures. And so what we've done is we've used a store passing style transformation to insert a set of addresses which we can then finitize. And as it turns out, all strategies for allocating these abstract addresses are actually sound. So all different possible ways of merging concrete addresses into abstract addresses gives us a sound analysis, and it turns out that we can encode different styles of context sensitivity and different styles of analysis by tuning our abstract allocator. So what we can do now is we can take our address set and we can finitize it, turning it into an abstract address set. And then all of the other semantic domains that depend on our address set also become abstract. And because we now merge multiple values into abstract addresses, we have to allow conflation between different closures in our store. So now we have abstract addresses mapping to a set of different closures. And we also have to allow non-determinism in our transition relation, because if we have more than one possible closure in call position, then we have to simulate multiple control flow edges stemming from that. So now what we have is a concrete initial state that we can abstract, and then we can iterate the same semantics except with this abstract allocator, and what we get is an iteration to a finite fixed point, which is a closed abstract transition graph. And if we take our concrete execution trace and we set it up alongside this, we'll see that it simulates in all cases. So this gives us both an easy way to engineer a static analysis like this, and also a proof of soundness for free by a tuning of our abstract address allocator. And what soundness looks like in this context is that if we have a concrete transition and an abstract antecedent, then we know that there must be some abstract transition which models our concrete transition, although there may be spurious ones. Go ahead.
Stupid remark. I recommend putting concrete at the bottom and abstract on top, stylistically.
Oh, within the...
Same diagram, just mirror it. We have concrete at the bottom. Abstract makes more sense than what that.
Okay.
Sorry.
I'll keep it in mind. So to recap at a high level, we take a couple of steps. We use a small step semantics, which basically means that our transition is exclusively in tail recursive form. And what this does is concentrates a form of unboundedness into many forms of unboundedness into one form of unboundedness. And then we do the same kind of thing in introducing a store passing style transformation, in that we concentrate different sources of unboundedness into one source of unboundedness. We then allow conflation of values in our store and non-determinism, and then we can use a finite abstract allocator to give us different styles of finite analysis, which models our concrete evaluation. And then from here we can layer on different styles of approximation and widening if we want. For example, we might use a global store, which over approximates all stores that we visit. So we join all updates into one global store. Or we could have a store for each piece of syntax, which would give us a flow-sensitive analysis, which is a little bit more precise. So now we can talk about Datalog a little bit. And this is the language that we want to encode these kinds of analyses into. So Datalog is a logic programming language, a non-Turing complete logic programming language, which allows us to encode Hornsat problems in the context of a deductive database. So what does this look like? Well, we have a number of relations, and we have a number of rules for our relations. And each rule says basically some atom, A0, is implied by the conjunction of some number of other atoms. And this is a horn clause because a horn clause is a disjunction of atoms where all but one of them are negated. And if we apply De Morgan's rule and then rewrite this, we can see that this is just the implication. So what we're able to do in bottom-up solving of a Datalog program is to basically find all of these implications, and when a set of facts applies, we can add the requisite fact that we need to. And so we can take a seed database that we get as input, and we can build it up to a database that minimally satisfies all of the rules that we provide. And so we can encode our static analysis like this. And a simple example would be a program that just has two tables, grandparent table and a parent table, and a rule like this. And what this says is, if A is a parent of B, and B is a parent of C, then A is a grandparent of C. And what we can do is we can implement this as a series of relational algebra rules, which we can run one iteration, and if we are given parent as an input, it'll give us grandparent as an output. So as I said before, our static analysis can be thought of as many interleaved transitive closure operations. So being able to do transitive closure in Datalog is kind of a CFA in microcosm in a way. And this is how we're getting started in exploring this problem. So we're gonna kind of focus in on the transitive closure problem. And transitive closure looks very similar to this example. We say, if there's some edge in a graph, AB, then there's also an edge in the transitive closure of the graph, AB. And if there's an edge AB in our transitive closure and an edge BC in our graph, then there's an edge AC in our transitive closure. And so we can encode this in relational algebra. And there's a whole zoo of different relational algebra operations that are out there. But we can take a minimal set and use it as a basis for solving Datalog in a bottom-up manner. So for example, we could just take these four operations. A union is the set union of the tuples in the relations. Renaming basically renames one column to another column, or reorders columns in the tuples. And this may be significant because in an efficient implementation, we may be keying on one of these columns, as we'll see when we talk about this algorithm in a second. And projection removes some dimensions from our relation. And natural join is sort of the heart of this, the most sophisticated. And basically what it does is it takes all of the different tuples and concatenates them such that the columns that they have in common have to match. And you can also think of this as generalizing intersection and Cartesian product. In the case where all of the columns match, we basically have an intersection operation. In the case where none of the columns match, we basically have a Cartesian product operation. So for example, if we take this Datalog rule that we talked about just a minute ago, we can implement this by taking as a function defined in terms of relational algebra, which takes in this parent relation, and it does a renaming on the parent operation to turn parent of AB into parent of BC with the same data, and then it does the natural join of that with the original parent, and it calls that G prime, and then it projects out the B column, and then it renames the C column to the B column, and then it unions that back into the result. So if we take this same thing and we look at it for our transitive closure example, then we have these exact same set of steps, except at the end we don't know that we're done, because this previous rule could always be completed in one step, and this we have to run to a fixed point. So we basically introduce a loop here, and we keep doing this, checking to see when t was actually updated at the end. So we run it until it stops being updated. And this is how we can compute transitive closure. And in practice, we would want another optimization on this, which is to add a frontier set. So what we would do is we would basically rename this last one dt, and we would keep it around. We would say, and then when we compute a join, we would also initialize it the way we would initialize t. And then when we compute a join, we compute the join off of the frontier set. This is because we only need to worry about the longest edges, extending the longest edges, because any edges shorter than that have already been extended and looked at in previous frontier sets. And this is actually a very significant operation. We've implemented both ways in one of our examples, and we thought it would be pretty significant, but it's like a difference between 500,000 duplicates having to be removed in an iteration versus 1,000 or something like that. So it's a huge deal. And then there's, of course, other optimizations we can perform. So now I'm going to talk about these two different approaches which have been recently published that we're trying to build off of. Both of them implement fast relational algebra, but they don't do it in a way that's amenable to a fixed point computation, which is what we need to do transitive closure or to do zero CFA or more sophisticated static analyses for functional languages, which would be interested in. So Redfox was published a couple of years ago by Haicheng Wu and a couple others, and we've been in contact with him to modify his code. He's been helpful. And basically their original algorithm was able to take these query plans, which would specify a number of relational algebra primitives using even lower level kernels, which could be pieced together to build up these relational algebra primitives. But it could only do a finite number of them. And there were a couple problems that they were solving which actually did require a fixed point computation, but what they did was just statically unroll these query plans to a certain extent in order to perform them. So we actually went in and did this the proper way by adding a conditional node that can check to see if a relation has changed, and then we update it and then we can loop whether we can branch on whether or not it has, and so we can introduce a loop. And then if you can see here, this is actually the notation that Redfox uses. So it's a little different. For example, they don't name the columns. They have columns in a particular order. They number them. If you want to do a project, you have to do a reorder to pull the columns you care about to the front, and then you call all the columns on the back. But other than these kind of superficial differences, it really is basically the basis of relational algebra operations that I talked about just before. And we use this to implement transitive closure on a fairly large graph. I think the transitive closure of the graph was 6.4 million nodes. And it's correct, we tested it. I wouldn't say that this is really representative of the kind of scaling that we would like to see or that we could get, because we haven't implemented this DT frontier set optimization that I talked about. So we ran into a problem with this, and we're getting some help from its original author, and we're still pushing on this. I think it's promising, but we don't really have the results to say that it's necessarily promising beyond being able to say that we could indeed add fixed point computations and get this to work. The other approach that we've been looking at is this hash join algorithm. So I'm going to talk a little bit about what this hash join algorithm looks like, and then talk about some of our initial results. So a hash join algorithm basically organizes the tuples in a relation into buckets. So here we have our Datalog rule that we've been talking about, transitive closure, and for the T, or in the faster version DT, we would have our set of tuples organized into hash buckets, and they're keyed based on the column that we want to match. So in this case, we want the B column in T of AB to match with the B column, or the first column, in G of BC. And so in our hash representation for T, we have them organized into buckets so that you can see the A values are all over the place, but the B values are mostly the same in the different buckets. Although in some cases we might end up merging different buckets, as would be usual for a hash table. And then we have the same thing for our relation G, and except it's being keyed based on the first column. And our tuples in G are a subset of our tuples in T, except they're in different buckets because we're keying them differently. So what we do is we're able to exploit the fact that if we're looking for values which match in B in the first bucket in T, we know we only have to look at the first bucket in G to find potential matches. And so we look at the different values for B. We take all the tuples that have that value for B. We find all the tuples that match in the corresponding bucket, and then we compute the Cartesian product. And so we get these 2 times 2 different tuples here. And we do the same here, except we have 2 different sets. So 1 times 1 and 2 times 1. We add them together. And then 1 times 3, and then 1 times 1. And then here 1 times 2 because we don't have a match for this tuple. Then next, we can take these tuples, and we can project out B, which is easy. And actually in our implementation, we just do this as we emit the tuples, because it's a rather trivial thing to do. But I'm showing it as a separate step. And then we have to do a reorganization. So now we have our renaming and unioning. And union is basically an insert, but as we do this insert, we need to reorganize it because we have to rekey our columns. So the significant thing in renaming our column C to column B is that here you can see they're still organized based on A, but no, they're not. They're organized based on the output of. They're organized based on the B that we've projected away. Sorry, so they're not organized in a particular way. But we need to reorganize them based on this second column. And so here we have tuples propagating into different buckets. So now, with this basis, we can talk about what a distributed hash join algorithm looks like, and it's really very simple. Basically, in a distributed hash join, this is from this paper, Distributed Hash Join Algorithms on Thousands of Cores from the beginning of this year. The real difference is that we can exploit the idea of matching up these different buckets at the granularity of specific buckets, and we can extend this to a coarser granularity of MPI nodes. So here we can basically partition our buckets in groups into different MPI nodes, and then in the core of our join algorithm, in our join algorithm period, we don't have to worry about any communication between the different nodes. We only have to worry about this. Yeah?
Still back in there, because there seems to be, you have a left recursive definition, T graph of AB is T graph of AB, and the graph of BC, is this going to work? Because it's left recursive.
So yes, it would work either way actually. So we could order it so we put graph of AB first and then transitive graph of BC, and either way it's going to work.
No, the
so
confusion is that basically the head of the clause is the same as the first, dissident of the clause.
Oh, that should be T graph AC.
Yeah.
T graph AB, graph BC.
Yeah.
It's just a type.
That's the bad.
right. Okay. I see. I'm sorry. Yes. So on the slides, I thought I'd caught that and renamed apparently all but this slide. I apologize for the confusion. But yeah, we could order this either way, and we'd just be extending on the front or extending on the back of our paths, and B is just a typo. So now, when we go to this renaming step, where we reorder things into different buckets, we actually do have to do communication. So we use the MPI all-to-all communication paradigm. And we have this one phase where we allow MPI under the hood to perform all the synchronization. And because we can't really anticipate which buckets are going to be transferring to which other buckets, we just have this one coarse phase of synchronization that we allow MPI to handle. And so we propagate all of the tuples to all the buckets that they belong in. Okay, so from this, I can talk about some preliminary results that we've gotten. We took a look at some graphs in the Florida sparse matrix collection. And this contains a number of graphs of different sizes, some quite large. And we took the largest of these, which is 412,000 edges. And it has a transitive closure of 1.6 billion edges, which if you compare against 400K squared is still pretty sparse. But it's a fairly large graph. And we computed this on the Quartz supercomputer at Lawrence Livermore National Lab. So it's not the fastest computer in the world, certainly, but it's got almost 100,000 compute cores, and we scaled it up to 2,048 cores. This is what our strong scaling looked like. So you can see here that we basically were able to exploit. We were able to exploit a significant amount of parallelism in the problem, up to about 64 or 128 nodes, at which point it really started to taper off. Up here, we're really getting a significant fraction of the ideal. So, for example, going from 1 node to 16 nodes, the ideal would be that we could do it 16 times faster, and instead we're doing it something like 6 times faster. But that still indicates, I think, that there's a significant amount of parallelism in just the transitive closure problem. And even more interestingly, as we scaled this up to 2,048 cores, we profiled it and looked at the timings for the different phases. So here we have, as a percent of the overall time, 4 different phases. The join algorithm, which happens just on each individual node. Then the network exchange, which sends the tuples to the correct buckets. Then the insert algorithm, which happens locally and just inserts it into a hash data structure on the local node once it's received. And then a fixed point check, which is another all-to-all communication that just says, has anyone actually seen a change? And then if so, we have to do another iteration. And what's interesting is that network exchange and fixed point check, as a percent of the overall time, is really a very small, nearly trivial proportion. And it kind of goes up and down until 2048 cores, 2048 nodes, at which point it doubles. And so our hypothesis for this is that because, or I should say Sid's hypothesis for this, is that because Quartz is a machine with a hierarchical network with different groups, up to 2048 cores, it was likely that we were only using intra-group communication, and that once we reach this size, we need more communication between groups, and so this slows things down. It's still much smaller than, it's still a small proportion of the overall time, but it starts to go up, and so I think we're starting to run into the machine limitations at quite a bit larger scale than we could exploit for this problem. And on other machines, you can actually select the exact allocation of nodes that you want, which isn't possible on Quartz, and so it should be possible to scale this up to tens of thousands of nodes on different machines, but possibly not Quartz. So I mentioned the Souffle Datalog solver. They use a very fast try algorithm. And one of our next steps we're very interested in is trying to hybridize the hash join algorithm with the try join algorithm by using the hash join algorithm at a coarse granularity to do MPI, and then using the try join algorithm from Souffle within each node. And we're working on doing zero CFA next instead of just transitive closure. I think we've kind of explored that as much as we can. We want to add this work list frontier optimization to Redfox. And in being able to do more polyvariant analyses, I think it's still a very open question that I'm thinking about. To what extent do we want to encode context sensitivity and polyvariance as a relation, or to what degree do we want to to what degree do we want to encode it as a rule versus to what degree do we want to actually write it out as a relation, which might give us more flexibility but might be more expensive. So those are some things we're thinking about, and I'd be happy to take questions and would love feedback. Thank you. Questions?
Well, could you extend that Datalog stuff to full logic programming on the GPU?
You know, with mini Cameron, it might just be possible, but otherwise. So I think to the extent that these relational algebra primitives could be used as a component of a more expressive logic programming language, I think it probably would be possible, and that would be very interesting. But I don't know that Datalog and these relational primitive operations being more limited could necessarily do everything we'd want to do. But it might be possible to hybridize it so that in some sense you could partition it and say under the hood there's sort of a transitive closure-like operation that's going on that's doing some of the work, and where we need something more sophisticated, then we do something else.
And could you also sort of generalize this approach to doing sort of general fixed point algorithms, or is there something about this that's only for abstract interpretation?
Oh, there's definitely nothing about it that's specific to abstract interpretation, but I think maybe the limitation would be what the algorithms could support. So, for example, the tuples should be tuples of data types that can be easily interned if they're not already natural numbers, because we need some finite. The underlying implementation is just going to use like a word of memory to store each of the numbers in the tuples. So if you wanted to have something higher order like sets within sets within sets or something, which actually we really would want to have to do this polyvariance. So this last point that I mentioned at the end, I think, is actually related to the question you're asking. If we want to do certain kinds of polyvariants, it'd be very convenient to have higher order environments in our analysis, which would then essentially require sets within tuples or relations over relations and things like that. And I think that would be really tricky because it would be hard to intern them. We'd have to do something like functional hash sets or something like that, and then intern those functional hash sets and then put those in tuples, and that doesn't seem particularly performant. Yeah?
This is kind of off the wall, but there's actually another way of formulating the transitive closure algorithm in Datalog, which is, so if you can go back to where you have some Datalog rules for transitive closure. The transitive case, rather than adjoining an edge to a path, can adjoin two paths. So instead of TAB, PBC, you do TBC.
Right, so
And
then you should
that
need like a
would be
logarithmic.
very different performance characteristics, does it?
Yeah, so then you would think you'd have a logarithmic number of iterations, right? But, so you'd basically be taking paths and adding them together, so the maximum length of the transitive closure would be doubling each time, right?
True.
So, so we did think about this, and I think the problem has to do with the keying that's involved. So basically, yeah, so you would think for parallelism that you could extract more parallelism out of it because you have less sequential work you have to be doing, right? Because each iteration does more overall work, in a sense. And then the iterations, which have to be sequentialized, the number of iterations is fewer. But the problem with this is that when we insert these t's back into t, we have to rekey them. But we only have to rekey them in one way. Whereas if we were joining t and t, then we would have to key on both columns. We'd have to have two different representations of t that we were maintaining as equal, but keyed in different ways. Does that make sense?
Yeah.
So we'd have to have two different representations, and at every insertion we'd be doing at least double work by inserting them into both of these and rekeying it. And I don't know how that impacts the performance. It's kind of unusual. We actually, we looked at this a while back, I think, in the context of Soufflé, and Soufflé generates a somewhat more complicated algorithm, which does what I'm describing. And it's actually much slower in this case, and it's very odd why. And I'd also like to know under the hood why that would be the case, because I would expect, especially if you have a lot of parallelism, if you have a lot of cores, that this would be a better approach.
Well, I think one reason might be you generate a lot more duplicates. And another reason is I don't think it's as amenable to the delta algorithm that you pointed out, where you just keep a frontier set. If you try and do the semi-naive thing here, the sort of keeping a naive set thing, you end up doing some redundant work that this somehow avoids. I don't remember the details.
Right. That's a good point. I think yeah, you do end up probably with many more duplicates. And then in addition, you have 4 inserts instead of 2 inserts, because normally you'd have one insert into T with keyed on B, and then one insert into DT keyed on B. And then in this case, you have 2 inserts into 2 different versions of DT and 2 inserts into 2 different versions of T.
So do you have a part that does the 0 CFA encoding?
In Soufflé I do, but I don't have this for our algorithm yet. Because we've been, it's actually been a surprising amount of engineering.
Down to the Datalog, and you have a sense of whether that sort of blows up or it works well.
Do I have a sense of how 0 CFA would be different from?
Well, so you have this 2 encoding steps, right? To Datalog and Datalog to relational algebra, right? So I guess my question is whether you've sort of gone through the whole chain and seen whether sort of the problem, it makes sense to do that encoding, or if the problem sort of explodes as you encode it that way. And the encoding ends up creating a very large relational algebra problem.
So, outside of exploring this with Soufflé, we've basically done this manually. We're just doing transitive closure, and we're implementing the underlying relational algebra and fixed point computations. So kind of small query plans like I was showing you for Redfox that will run through a series of steps and then take a loop. And we've handwritten all of that, so I don't see why it would be different to have a number of rules. So 0 CFA written in Soufflé is like a few dozen rules, and it might get more complicated if you had a more sophisticated analysis. But it's not. In principle, you could even probably do it by hand, and I don't see why it would be so fundamentally different. I think that the parallelism could look different, but I strongly suspect, my hypothesis is that there would only be strictly more parallelism to exploit than just the transitive closure operation. But no, all we've done so far experimentally is transitive closure that we've written manually using our own hash join algorithms.
Cool. Time for one more question. All right, well, let's thank you.